All right, so today we have HPE. They're going to give us a talk about their work. And without further ado, I hand it off to Namit. Go ahead.
All right, thank you, Amir. All right, welcome everyone. The plan today is to tell you about HPE's application-centric quantum supercomputing framework, and we'll kind of split this talk 50-50 between myself and Michael. And so, Michael will interrupt me rudely in the middle of the talk and then take over from there. And yeah, so let's get into it. I'm not going to do a review of what computers are good for. Sorry, someone is typing. If they could mute themselves. Yeah, I'm not going to do a review of what computers are good for because presumably everyone here already knows them, and I'm going to just start to talk about accelerating very specific class of problems, which is quantum simulation. Right. A large part of what we expect quantum computers to be good for is to simulate Hamiltonians, to simulate quantum mechanics itself, but in a more non-trivial way, in the sense that these can be error-corrected computations, right? And so what do typical quantum simulation workflows look like? Well, you have to do a bit of pre-processing where you first identify the Hamiltonian, the material, the chemistry problem that you want to simulate. And then you maybe want to estimate the ground state energy of this problem. Okay. And so typically what I have in my mind is something like quantum phase estimation, where you prepare some ground state approximation of this problem. You submit it to your quantum processing unit, you prepare that state, you do energy estimation, and then you do a bunch of post-processing. You will see that in this kind of, and then you repeat for other points in your phase diagram or something. You will see that in this workflow, I have kind of put a conventional HPC in the beginning. Well, for quantum phase estimation, as we will discuss in a little bit, one of the most important parts is that you need a good reference initial state. The quality of the initial reference state kind of determines how many iterations of phase estimation you need to do. And so it's kind of quintessential that you build a good one. And, there is a bit of a chicken and egg problem here in that the problems we are trying to use computers for are very hard themselves. And so preparing good reference initial states itself is a hard problem. So you kind of need a small to medium-sized cluster just to prepare a good reference state that you can then prepare on to optimize this thing, prepare on your QPU and do phase estimation. Now you may say, oh, but there are other algorithms that may not need to do that. Well, it turns out for a lot of them, you will need to do some kind of HPC in the post-processing part. So something maybe you have in mind, sample-based quantum diagonalization routines. So you don't need maybe that much emphasis on the initial state, but you will pay that sort of price in the later post-processing part, right? So I have this kind of workflow in my mind, and that's what we will focus on. So I'll give you two examples of this later in this talk, one on electronic structure and one on Fermi-Hubbard. Okay, great. An important disclaimer before I get into more details of the talk, which is that our work, our discussion today will be primarily focused on FTQC, basically on quantum error correction and quantum error corrected computers, as opposed to more NISQ-based discussions. A lot of our techniques do apply to NISQ, but our focus is primarily on QEC. Okay. And part of the reason is that we're interested in computations which can be quite non-trivial. And as we know, the way noise is in current hardware, you're kind of restricted to something like log n depth, right? You just, after that, everything kind of scrambles away, right? So you need QEC to go beyond this log depth boundary, log depth barrier. And at the same time, QEC adds an additional layer of complexity. So for example, you have to redundantly encode your noisy qubits to create a more stable, less noisy logical qubit. And there are additional new challenges. So for example, we know that you cannot just apply all the gates that you used to do in your compiler, where you just applied an RZ gate whenever you wanted, because QEC theory tells you that there are no universal fault-tolerant gate sets. And so there are a subset of gates that you will always have to treat it separately. Historically, these have been the rotation gates, and so they need to be first approximated, and then they need to be kind of distilled and injected in this. So there's some protocols for that, right? So a consequence of that, from the point of view of building these systems and let's say building compilers and schedulers, is that you have to change your focus on let's say, minimizing C-naughts, which has been the focus of NISC, because you need to minimize entanglement, and those are the noisy gates, to something like minimizing T-gates, minimizing rotation gates. Okay? So it changes how you compile your algorithms. Okay? There are many additional layers that show up, and one of those is the real-time decoding requirements, which become quite significant. And as we want to build systems which are quite flexible in their QEC capabilities, so I'll discuss why you may need even more classical compute than you may have anticipated. Okay. So that's what our focus will be on: QEC-based algorithms, QEC-based compilers, and the new challenges that come with them. And so that's what I'll get into. Okay? I think it'll be useful at this point to have one slide about real-time decoding, because the classical compute for this is quite significant. And so this is a rough summary of a lot of the QLDPC-based decoders that are out there in the literature. And the reason I chose QLDPC codes is because they promise much better encoding rates. And given that, we are still kind of stuck at about 100, order of 100 physical qubits, encoding rates are very, very important in being able to do larger computations. And so it's very likely that we may end up focusing primarily on QLDPC codes in the future. And what this kind of this figure is about is to highlight kind of the different trade-offs. You have trade-offs between accuracy, latency, and hardware usage. And so depending on your requirements, you may need things which are relatively fast, hungry for the hardware in some medium way. And if you want something that's lightweight on the hardware side, well, it turns out to be quite slow. So there seem to be these immutable trade-offs between generality, speed, and accuracy in decoding QEC codes. And part of the reason that is that minimum weight perfect matching is NP-hard, right? So you just cannot have this kind of universal thing. And so as QEC research kind of evolves today, we want to make sure that we are building a system that supports kind of new insights into these things, that supports new QEC codes, and that supports your solvers on CPUs, GPUs, FPGAs, and so on. Okay, so that's the kind of system we want to build. All right. So with this kind of preamble, I'm now happy to get into my talk, and the first kind of application instance in mind, which is distributed quantum chemistry, in particular electronic structure simulation. Right? So the first question you must ask yourself is, how do you actually distribute quantum circuits? It doesn't seem that obvious at first glance, but there are roughly two types of techniques, which is that anytime you encounter a 2-qubit gate, you can either use shared entanglement, namely you prepared belt states between two QPUs and you consume them to implement a 2-qubit gate, or you do something which goes by the name of circuit knitting or adaptive circuit knitting at times, where you just treat the two QPUs as independent processing units, and in post-processing, you patch up your results. Okay? This has a number of limitations, perhaps the most famous one being that typically the cost incurred is exponential in the number of 2-qubit gates you cut. Right? But it turns out, like a lot of exponentials in nature and in real life, some of this can be more due to poor algorithms, and I'll give you an instance of that. Okay, so my goal is not to distribute arbitrary quantum circuits, but my goal is to distribute Hamiltonian systems which have locality, right? So if I give you a Hamiltonian system, it shouldn't just be controlled by the number of 2-qubit gates, my quantum simulation overhead with circuit knitting. It should have something to do with the strength of coupling across the boundary, how much subsystem A talks with subsystem B. And so by doing a more careful analysis, you can show that the cost is exponential in this term eta, which is the strength of the boundary Hamiltonian, namely how much the two subsystems talk to each other. Okay. There will be a second insight, which has to do with, again, moving away from this gate by gate cutting. So let me provide the second insight, which is that really finding optimal locations to cut is about finding entanglement. Okay? So what does it mean? So imagine I give you some Hamiltonian you imagine you have a 1D lattice, okay, and it's a translationally invariant system. What does it mean? It means that everything looks the same everywhere. That's what translation invariance is. So it doesn't matter where you cut, because you're equally worse or equally better everywhere you go. Right? But a lot of systems in nature, a lot of systems in real life are not translation invariant. They have disorder, they have defects. And so real systems are going to be heterogeneous. Right? So looking to the left is different from looking to the right. And when you have these heterogeneous systems, if you look at how their spatial entanglement entropy profile looks like, what you will find is that that is also heterogeneous. And the cost of cutting across some location in quantum simulation is determined by the entanglement entropy across the boundary. Okay, so imagine that you have a region of high entanglement. Well, the distribution complexity, how much you have to pay in post-processing, is determined now by that function of entanglement in some sense. Similarly, if you find a region of low entanglement, well, then the cost you have to pay is lower. So this is the general insight that if you want to distribute quantum simulation, you want to make sure that you do it based on entanglement and not just in some load balanced way where you're just thinking about doing a 50-50 cut. Okay? So finding optimal cuts is really about characterizing entanglement. This problem was very clear for us from the point of view of studying quantum spin chains, because they have a nice tensor product structure. They have a nice lattice structure in your mind. But as you start to go to more complex problems like quantum chemistry, maybe some of this structure is not that obvious. So I'll show you in a second how we kind of generalize this. But I'll take a quick pause if there are any questions. Okay, so no disagreement with using entanglement to find optimal cuts. All right. So electronic structure Hamiltonians are basically, some way to describe how electrons are hopping on a bunch of orbitals. For all intents and purposes, you can just think of them as kind of some generalized lattice, and you have electrons hopping around, or you have electrons kind of repelling with each other, right? And so let's say I want to take such a Hamiltonian and I want to distribute it. Well, how do I do that? Well, first, let's try to use something simple like first order Trotter formula to write down what the time evolution operator looks like. In most quantum simulations, in some shape or form, you're simulating this object. So I want to keep that. And the reason I choose Trotterization is because I really care to preserve the structure of the Hamiltonian. If you just use something like qubitization-based things, while they may have kind of optimal asymptotic complexity, first, they kind of wash away the local structure of the Hamiltonian, which is really, really bad in many cases. And for small problem sizes and for a lot of physical problems, this is not the optimal scaling. Okay, so once you preserve the structure which shows up in Trotter simulation, you see that this time evolution operator is nothing but alternating sequences of Gaussian layers followed by Coulomb layers. Okay, these Gaussian layers, it turns out, are extremely special. Right? They are, you can, for all intents and purposes, you can think of them as the fermionic equivalent of stabilizer states, fermionic equivalent of Clifford gates. And as many of you may know, Clifford gates are very special in computing. In fact, we kind of think of them as free. Okay, so it turns out that these Gaussian unitaries, which are very important in electronic structure simulation, also have a notion of being free in some sense. So in kind of one line, the main thing we observed when trying to distribute electronic structure circuits was twofold. First, that for Gaussian layers, it is extremely easy to characterize the distribution cost of these orbital rotations. Okay, I will show you that there is a way to do this exponentially better than people have done before. And for the Coulomb layers, it turns out that they almost always have order one distribution cost. So you can almost be like, oh, it's very easy to distribute them. Okay, so these are the two insights we had, and let me provide them one by one. Okay, so the first insight was really for us was that if you have these Gaussian unitaries, then if you do gate by gate cutting, you incur a cost that kind of goes super exponentially. It goes like x to the n squared. While if you use our method, which is to treat Gaussian layers with their so-called covariance matrix formalism, you can characterize their distribution cost not by an exponential size matrix, but by a linear size matrix. So this is an exponential improvement in characterizing their cost. And then you can show, I can give you an explicit algorithm for how to do this in a cost that scales only xn in the worst case. Okay, so this worst case cost, in practice, you expect to be able to do much better. The second thing we noticed is going back here where you have the Gaussian layers and then the Coulomb layers. For the Coulomb layers, what you notice is that if you start to look at how entanglement in the Coulomb layers is, these things naturally have disorder in them. And so when you try to cut them, they kind of have a localization within each fragment. Each Coulomb layer kind of localizes itself. And what ends up happening is that the cost of cutting them is kind of order 1 for all relevant timescales. Okay, and part of the reason, part of the way we were able to notice this is to show that these Coulomb layers, the entanglement in them, simulates or behaves a bit like many-body localization, which is a well-known phenomenon in physics, where when you have disorder in a system, the system basically behaves almost like a quasi-integrable model, namely everything is localized, things don't move around as much, and you have a more efficient description of the systems. For me, part of this discussion reminds of the previous talk from Luke last week, where he was also kind of hinting at, oh, look, there may be a more efficient representation for these quantum chemistry problems. And for us, that kind of emerged naturally in the Coulomb layer, where we see signatures of many-body localization. Okay. So now I know that this may seem like a very physics discussion, but the point is that once you start to take into account the physics-based structure of these problems, you see that there are exponential reduction in characterizing them, maybe quadratic reductions in the cost of distribution, and you get novel algorithms for how to do these things. So a lot of the hardness of these problems may be slightly mischaracterized. Okay, great. And then we went on and we kind of did some benchmarks for small molecules, etc. And we see that having this kind of more efficient characterization in mind, more physics/chemistry-based characterization, and having the application-based mindset, namely that the accuracy to which you want to characterize your problem, these things give you orders of magnitude reduction in your distribution complexity. That's kind of the purpose of this talk. Okay. All right. So together with these results, which I know I didn't go into too much detail in the interest of time and complexity, we have sort of new workflows where we want to have this kind of concurrent compilation going on in your HPC system, where you're constantly simulating the entanglement structure of your electronic structure trotter circuit, and then using that to find optimal low entanglement cuts, and always distributing across those. And the good thing of our framework is that you can simultaneously use the same framework to estimate both the overhead for adaptive circuit knitting or more classical networking, and also roughly the logarithm of that gives you the cost of how many bell pairs you would need to do shared entanglement and to do quantum networking. Okay, so you have this one framework where you have a classical sort of process running on the side, finding these low entanglement cuts and using them to distribute your quantum simulation. All right, great. Okay, so this is all nice and well, but how about we get into some more concrete numbers and start to think about if you want to actually simulate interesting problems on fault-tolerant hardware, what kind of sizes do those translate into? And so I will reference one of our papers from earlier this year, which was trying to understand basically trade-offs between full QEC versus something that is known as partial fault tolerance, partial FTQC, where you treat a subset of your computations in a non-fault tolerant way, and it helps you reduce the qubit requirements. The numbers I'm going to show you here are not those. These are full FTQC numbers. Okay. So what we noticed roughly in this research estimation is that if your problem sizes are kind of small, maybe like six orbital problems and so on, the runtime of these things can be kind of small in the order of seconds to minutes. And so you can ask yourself this question: can I take a large quantum chemistry problem and can I distributed efficiently into these order 6, order 10 orbital problems, all of which can be handled on an FTQC hardware in some reasonable runtime, do those things, patch them up together, either via adaptive circuit knitting or with shared entanglement generation. And if these kind of workflows are some things you can do, and a lot of it can be understood in pre-processing, in your classical pre-processing, then you have a new kind of workflow. And what this translates into is that you're looking at quantum computations of seconds to minutes, maybe hours, depending on how big a block you actually want to run in one go. But notice that as your number of orbitals you keep in one fragment increases, the number of logical qubits you will need in a single chunk also begins to grow. So you want to understand these trade-offs. And the runtime of these things are, of course, a bit more optimal in the sense that they are for superconducting qubits, so they're the fast qubits. These runtimes are going to increase quite a lot as you go to slower qubits like neutral atoms and trapped ions, right? The second thing, which I will talk about in a bit more detail now, is that how long is the classical compute that is needed for these things? Again, I will show that if you want to prepare good initial states, there is non-trivial classical compute that can go into these problems. And there may even be some concurrent computation going on to track your entanglement boundaries as you're doing the simulation. There is some reasonable interaction between the quantum and classical side, and the number of iterations is really a function of your accuracy requirements. Okay, so in general, the kind of the requirements is that communication on the order of seconds is great. It would be really helpful to accelerate these kind of simulations, but waiting for hours to days may not be ideal. Right? In fact, it could kind of ruin this kind of workflow that we have in mind. Okay. So before I go to the next slide, maybe I quickly pause for some questions.
I do have a question, Amit. So regarding the entanglement, and this was probably a question for earlier, do you use any like tensor network like law to inform how this distribution is made? I'm sure you've thought about it.
100%, yes. So both for the spin chains and more kind of non-trivial problems like electronic structure, we realized that actually thinking about what are optimal representations of problems is really the key insight. Like, not everything should be represented in some gate by gate way, and you're losing all the structure of the problem when you do that. But in most cases, in particular for these disordered systems, tensor networks allow you to simulate them to really large times. And so the better your classical simulation techniques, the better you can track your entanglement boundaries, and the more it informs you where to distribute your circuit. And similarly for electronic structure, we also noticed that once you have many-body localization, it induces a certain type of tensor network structure in your problem, and you want to use those for your simulation. In fact, we hope to have a paper coming out highlighting this kind of new structure in a couple of weeks. But yeah, that's exactly right on money, that these inspired their own tensor network type ansatz.
See, that's pretty cool. A second question. So I noticed that in this slide you say you use first order trotter. Is that a choice because you're using just like a toy problem? Is this enough for your simulation? Do you have any idea of like how does it change your cut locations or your entanglement profile?
Perfect. Yeah. So great question. I think that in general, you could certainly do second order trotter here. But what we noticed, in a certain sense, the good thing with trotter, first and second order trotters, is that you really need to play around with how small the delta t's you're playing with. And if you choose a sufficiently small delta t, which we do, this is pretty good for pretty much anything you would want to do.
It doesn't make a lot of sense.
Yeah, and this already exposes the main thing I wanted was to highlight the Gaussian and the Coulomb structure in there. Once that is exposed, I can deal with them independently as a physics problem. The Coulomb thing with many-body localization, the Gaussian with this covariance matrix formalism, and sort of efficient characterizations of both. Second order trotter will basically just do this in a forward way and then sort of backward way, and then, but it roughly gives you the same structure.
Thank you.
I think I'm approaching the middle of my talk, so maybe I'll give one of the highlight slides quickly, and then want to leave some time for Michael. But you can ask. I'll talk a little bit about initial state preparation in a moment. But one of the things you can ask is, how bad could this cost be for hard problems? And it turns out that this could be really, really non-trivial. So, for example, problems like FEMOCO, iron sulfur clusters, and so on, these are really some of the most interesting problems we could want to solve with quantum computers. And if you really sit down and do calculations, as has been done in this really, really nice paper from earlier this year, you realize that you may need runtime at least of the order of, I mean, these numbers are kind of ridiculous, right? Because they are like 2 seconds on all of Frontier. So I'm not proposing you do that, but let's say you prepare an initial state with 10% overlap with the true ground state. So you divide it by a 10th this runtime. That's still a lot of classical compute. And so what you may want to do is to, I don't know, build a small to medium-sized cluster, which is primarily focused on optimizing the initial state, the overlap, and then you ship it off to your QPU, prepare it, do phase estimation, send it off. Or you don't want to do that, you want to do SQD type things, well, you will need to do a lot of post-processing later on anyway. So in some sense or the other, these are a good approximation, a good placeholder for the kind of classical compute that is needed. Okay, so these can be quite non-trivial. And I feel that my point is not that, oh, you should use this number as a placeholder. My point is that I think we're underestimating the cost of initial state preparation. Okay. So in the interest of time and in the interest of emphasizing this point further, I'm going to quickly run through some of the Fermi-Hubbard thing, and let me just point out how much the initial state problem is ignored in literature and discussions today. And so once again, let me mention that the only mode of failure for quantum phase estimation is that you prepare a bad state. You prepare a state that is orthogonal to the ground state, and you just don't get any signal, right? But as long as you prepare something that has some overlap with the ground state, you're guaranteed that if you repeat phase estimation inverse overlap number of times, then you're going to learn the ground state energy. You're going to learn that phase that you're interested in. And if you try to do this for even small iron sulfur cluster problems, you can show that the cost of preparing these initial states can be as high as 10 to the 10 Toffoli gates. Okay, so this is, for reference, this is even worse than the actual phase estimation algorithm you may want to do in some cases. So initial state preparation is a non-trivial problem. I don't think we should just hide it under the rug when we do resource estimations, as the kind of the community has been doing forever, and we need to be more careful about it. And one of the ways that we are thinking about optimizing these costs and being more upfront about it is to think about dynamic circuits. The key idea here being that if you use measurements in feed-forward circuits, but not just at the physical layer, but at the logical layer, you can reduce your state preparation cost by, in some cases with some good guarantees. So, for example, if you want to do long-range CNOTs in superconducting qubits, you can go from a circuit with order n depth to order 1 depth. So this is a n to 1 reduction. If you're interested in preparing tensor network states or MPS states, which is what typically one does for Fermi-Hubbard simulation or chemistry simulation, then these things can also give you an exponential reduction in depth from order log n to log n. This is non-trivial. It really uses the structure underlying these initial states, which is that of something called multi-scale entanglement renormalization ansatz, and you use that to reduce these costs. And if you do that, I'm hopeful that one can take these 10 to the 10 Toffoli gate initial state costs and reduce them significantly, where you can actually do quantum phase estimation on these problems. Okay. With that in mind, I am going to kind of pause here and just kind of give it to Michael with roughly the same emphasis that you need to do dynamic circuits, you need to do adaptive circuits, because they seem to be one of the best known algorithms to prepare these kind of quantum states efficiently. Okay, so I'll quickly pause for questions, but if not, I'll pass it on to Michael. All right, great. So off to you, Michael.
Okay, slides coming through, okay? And I'm going to turn on my myself so you can see me. Okay, great. So this is sort of part 2 of the talk. And thanks, Namit, for describing electronic structure, distributed simulations, and a little bit about Fermi-Hubbard, and reminding everyone why adaptive circuits are important. And again, at the logical level means we're talking about the circuit before you apply error correction, sort of what the algorithm thinks of as the circuit, not necessarily something about quantum error correction. So I'm going to talk about mid-circuit classical computations. And I'm going to start by talking about quantum Fourier transform, and then I'll talk about Oracle sketch and some future algorithms. So quantum Fourier transform is one of the most important quantum subroutines of all time. It's at the core of almost all exponential speedups we're aware of in quantum computing. And many of these algorithms use an inverse quantum Fourier transform followed by a measurement, which I have sort of a picture of over here. We, in playing around with some adaptive circuits, we were excited to discover a way to reduce the gate count of quantum Fourier transform followed by measurements from order n squared gates. Like you'll notice here, there's sort of a sequence of about n rotations on each qubit. We can reduce that to order n, and n is the number of qubits, n rotations. And we learned that this actually was a known result that we had rediscovered, but I'm talking about it now because it has real implications for fault-tolerant quantum computers' system design. So let's look at this. Let's look at this a little bit. First of all, what would be maybe an initial system design? Because I'm going to talk about the implications for system design. So we're sort of our starting point. So our starting point is there's some kind of client node. It sends entire circuits over to a quantum resource, and somewhere in there they get compiled for including error correction, and real-time decoding happens and all of that. It gets run and we get measurement results back. And these circuits, we're assuming that they can be adaptive circuits for the reasons Namit already explained. Algorithmically, we can get orders of magnitude improvement in our runtime if we can use these adaptive circuits. So we need the adaptive circuits. And here I'm going to say in our initial design, we're assuming that the adaptive circuits mean that there can be classical computations that manage the circuit, things like mid-circuit measurement, feed forward, as long as they are applying to as something that is simple enough that it can run within the control electronics. That's more or less the situation we have today on NISQ devices, that if you're doing adaptive circuits, those classical components are running within the control electronics. And if you know of cases where that's not the case, I'd love to hear about it, maybe at the end of the talk or later on. So here's a figure from one of the key papers in electronic structure simulation. And this has a quantum Fourier transform inverse followed by measurement, just like before. And we realized that in this paper, when they describe the resource estimation for how long the algorithm takes, they assume that this quantum Fourier transform can be done in order n gates actually, rather than n squared like the sort of textbook version, using an adaptive circuit. And this adaptive circuit is called the semi-classical procedure from this reference 2. So my claim is that you can't run this adaptive circuit in that initial FDQC system design I just described. Let's look at that adaptive circuit and we'll find out why. So first we'll start with that quantum Fourier transform followed by measurement, just like what you'd see in the textbook. And I'm leaving out swaps, and I might have put my bit order in a reverse of what people are used to, but that doesn't really matter for the arguments I'm making. So then the next step is we realize that measurements can compute with these controls. So when a measurement is after one of these controls, we can move the measurement ahead of it, and that changes the controls to classically controlled gates. So now these are conditional, so meaning that we do the measurement. If the measurement was 0, then we don't run this rotation gate. Let's see if I can get my, oh no, you can get my slides to advance. Okay, there we go. So then the next step is to realize, since these are all classically controlled conditional rotation gates, we can combine them. And we can now have a process where we do a measurement, we get some measurement value, and then we do a rotation gate that's a function of the previous measurements. There are these light arrows here that show the sort of data flow where every qubit is measured, and then the measurement values from all qubits measured so far contribute to what angle we will do when we do this rotation. So now we have, instead of order n squared rotation gates, we have n-1 rotation gates, because there's only one rotation gate for every qubit, and we didn't need one for the first qubit. So this is the semi-classical procedure, sort of re-derived in a way that maybe modern quantum computing people will make sense of, and that's sort of that's what we have, is these rotation gates with angles based on the measurements. So now, why did I say that that is impossible with that initial system design? Well, those angles depend on the measurements, and in a fault-tolerant quantum computing system, we can't just do an arbitrary angle rotation. We need to approximate our rotation gates with a sequence of gates that makes what I'd call an approximating sequence. Now we need to, if we're trying to run this circuit, now we have to compute those approximating sequences while we're running the circuit. So say we're trying to do this gate here, we get all these measurement results from the previous ones, we do some math, we have to come up with this approximating gate sequence, and there's, as far as I can tell, absolutely no way you could do that in control electronics. Current algorithms for it take something like 4 milliseconds on a laptop. So it's not possible with that system design that I described as the initial or assumed system design. Instead, we need some kind of relationship between the quantum resource and some kind of classical compute resource that is helping, where the quantum resource can send the measurement results, and this classical compute resource can send back the gate sequence to approximate that rotation. Any questions on this part? This is sort of one of my big claims.
I have one quick question.
Yes.
This interaction doesn't have to be within the coherence time of the logical qubits, or does it have to be within the coherence time?
So logical qubits don't, I mean, we have physical qubits have a coherence time you're used to. Since they're error corrected, we are not as worried about it. The logical qubits have a significantly extended coherence time. We could talk about what it is, but the whole point of error correction is that we'll extend it to, you know, a couple days or something like that, depending on, you know, what amount of error correction we apply. So it's not the same level of time scale, and I have some discussion of this later, because we're talking about the logical level rather than the physical level. So there's more time for these approximating sequences to be computed.
Sounds good. Thank you.
All right. Let me. Oh, go ahead. Is there another thing?
Yeah, quick
Yes.
thing.
So
Yeah.
the key.
Go ahead.
So the key revelation here is that basically, it's sort of a mid-circuit measurement like thing there, but and the logical thing where sort of coherence time is not assumed at the moment to be a limiting factor. It's bringing all the sequences out into some computational platform for the approximating sequence and bringing it back. Is that the kind of the insight at a high level?
Right. So this means that there's additional interactions between, let's say, quantum resource and HPC nodes that we weren't in my initial picture. And my initial picture, I was trying to draw what I sort of see as what everybody is assuming the system design will be. So whether or not that's true or not is sort of beside the point. But now we have a specific case that that applies in many algorithms. Okay, so next I'm going to show you how actually we can do. We don't actually have to send these sequences as a list of gates and then have them be recompiled, because recompiling in FTQC would be a significant burden. So what we can do is make one change to our initial system design, which is to add the ability to send measurements mid-circuit to some kind of helper resources and to receive some classical condition values from the other resource. So I'd call these externally controlled conditional gates. So the way to do that is to make use of Matsumoto Amano normal form for single qubit unitaries. This is a regular expression of if you make a bunch of gates in this pattern, you can do any single qubit unitary at all. So this is sort of a repeating pattern, we can turn it into a loop. And if we classically condition all of these, not by anything in the circuit, by what the gate sequence computed by our helper resource is, then we can represent any rotation. And then here there's a Clifford gate. We can do a similar thing for the Clifford gate. So down here I have an example. This is one of these gate sequences for some rotation. I'm assuming that maybe we didn't have the ability to literally do a loop that terminates wherever we want. Maybe we knew that we needed to make space for 12 iterations of these to reach our error bound. Then we can use this bit sequence. And if you look closely, you'll see that every time there's a 0, that gate, if we leave it out, will really result in this sequence above. And I'll note at the end, there are a couple of repetitions of this loop that we didn't use in our sequence. We are just using 0. That's why every gate is classically conditioned, instead of just, if you look at this formula, you might think I would only need to do the S gate. So using this strategy, we can extend systems that people are already building today without having to do drastic re-architecture in order to support this kind of pattern. So you might be wondering, oh, well, that's an interesting idiom of externally controlled classical conditional gates. Are there other algorithms that would use that idiom? And we'll talk about one. So you might have seen this recent paper about quantum oracle sketch. It's called Exponential Quantum Advantage in Processing Massive Classical Data by a number of authors, including Preskel and Wang. I've reproduced a figure from that paper to the right. They have lots of exciting and maybe contentious claims, and you can see they're having some fun putting data centers in robots. But at the core of it, what is going on in here? They want to have they're describing a method to approximate a large data set in a quantum state, and they're doing it in a way that's provably using less space, not time, but space, than any classical algorithm. So what's the circuit at the core of this? Well, we have a situation kind of like this circuit up here on the right. So we're approximating a function. We take in an integer. and it produces, the function takes in an integer and produces 0 or 1. So these are just n-bit numbers. And what their algorithm does is we apply a bunch of these multi-controlled phase gates. The angle in the phase gate is an algorithm parameter, and the controls are determined by the integer. And we only do this for the cases where our function returned 1. So this is these sort of, whether it's a positive or negative control, is going to be determined by this xi value. And we can use the same externally controlled conditional gates mechanism. Here I've drawn just one of them, but this would repeat 7 times to show this pattern above. And you just send, well, classically condition this gate to be not run if we had a regular control, and we would run it if it had an inverse control, and we just make sure to do the same thing on the second half of this circuit. The result is now we can have an external to the quantum resource data sampler. Their paper is about massive data and doing random sampling from some very large data set, and then using that data to create a quantum state approximating it. So we need to have potentially very large amount of memory or other compute resources on the data sampler. Again, wouldn't fit into the control electronics, but we can send these values over as those externally controlled conditional gates in order to do this kind of algorithm. Okay, and then I have one other example, which is a little bit more of a framework for algorithms. So quantum singular value transform is a key building block within the most optimal quantum Hamiltonian simulation that we know about today. And authors of this paper on feed-forward QSVT, their feed-forward QSVT fits into a general framework that they drew a picture of over here. Anything that would fit into this general framework in terms of a future algorithm, you can see there's some sort of parameters coming from the classical computer into future gates based on previous measurement results. How complicated that computation is to compute these gates is sort of a key question in terms of whether or not it could be in the control electronics, but I wouldn't expect that everything would fit into the control electronics. So anytime we have something where computing the actual logical gates we're doing needed more compute than available in the control electronics based on those measurements, we need this kind of mechanism that I'm describing. We anticipate that there are likely to be feed-forward quantum machine learning algorithms that would fit into this kind of scheme. And in that case, not only would we be computing these approximating sequences for different angles that we're computing for sort of future gates in our algorithm, but we'd also be running a classical optimizer in some kind of short time scale in order to compute what those angles are. Okay, so from here, I'm going to go to sort of summarizing the implications for system design of all of this presentation. I'm going to try and go through that quickly and then leave some time for questions. So Namit already talked about the Fermi-Hubbard and distributed electronic structure simulation. We see that the compute requirements can be significant on the classical side, but it would still be useful to have a small or medium-sized cluster to do those, and that cluster might be associated with a quantum computer. And the quantum circuit runtime, it depends on what you're doing, ranging from seconds to days. And then all of these algorithms can have a bunch of iterations between classical and quantum, depending on what you're doing. On the part I was describing about logical mid-circuit classical compute and those adaptive circuits, We saw that with Fermi-Hubbard for state preparation, the classical compute probably can be done within the control electronics, but we still think it's important to emphasize that it matters. For quantum Fourier transform followed by measurement, it would be too much for control electronics. The current code that does this took 4 milliseconds on a laptop, but I expect that could be significantly optimized with parallel resources to bring it to something closer to an FTQC clock speed. We saw that Oracle sketching also had similar needs for mid-circuit classical compute. In this case, sampling some large data set that wouldn't be possible in the control electronics because the data's we would expect too big. And then for future algorithms, we don't know what they'll all be, but we anticipate feed-forward machine learning, and we anticipate that not all yet to be invented algorithms would fit into the control electronics need for simple classical compute. So then if we think about the sort of latencies involved in these FTQC systems, over here is the sort of key thing for superconducting neutral atoms and trapped ions. I've listed expected fault-tolerant clock speeds, and be aware that there is also a measure of time, the reaction time, that is also important and might be significantly higher than this, maybe 50 times higher in some cases. But FTQC clock is a good starting point for thinking about these latencies. So if we have something connected with an HPC network, it's on the order of magnitude of these FTQC system clocks. So when we're doing logical adaptive circuits, that's reasonable. If you said, oh, well, we'll just use a carrier pigeon to connect those systems, it would, your pigeon would take maybe hours to move the data and get lost on the way and then take a few days. That would be completely unacceptable for these mid-circuit applications. So anything like an HPC network makes it very feasible. Anything where you'd wait in a scheduler queue, any of these long time scales would make it infeasible. And the timing impacts both the application, the speed it runs at, and also the cumulative logical error rate, because anything you do in a fault-tolerant quantum computing, any gate you run, adds a little bit of potential for fault, for more errors over time, because the logical error rate won't be 0. It'll be lower, but it won't be 0. Our goal is to design for flexibility informed by those applications we were just talking about. We want to make a single quantum supercomputer, integrated quantum and HPC system that supports all the applications we talked about and future applications. Here are some goals that I'm not going to read over right now, but might be interesting as we're coming up with requirements. But they're based on those same applications. We'd like to be able to do mid-circuit, non-trivial amounts of classical compute. We'd like to be able to do explorations of quantum error correction, maybe not as efficient as what's built into a quantum resource, but available for people to do experiments. And also, we think it's important to have the ability for customers in using one of these systems to put in specialized hardware. If somebody realizes that there's a classical compute piece of one of these workflows that's really slow today, then they should be able to explore using new hardware such as machine learning specific devices to try to accelerate that. This is something that will require custom hardware, and in HPC context, we're used to that. As long as we can talk on the same network, you can have wacky, weird hardware on some nodes. In terms of hardware, we're envisioning quantum resources with co-located HPC nodes and a low latency network connection. And in terms of software, we want to build upon the work people are already doing and extend it to support these mid-circuit classical compute needs on those HPC nodes. And here's the final slide, which has a little cartoon picture of what I just described in terms of hardware. which is hopefully completely unsurprising. There's a bunch of HPC nodes with a variety of hardware in them. There's a quantum resource that has some fault-tolerant quantum computing capabilities built in. And then we can use the high-performance network to cover those cases where flexibility is needed. And here's a cartoon, sort of, we'll say, artist rendition of a future quantum supercomputer where there might be multiple QPUs and some racks of classical compute. And I'll end with just the remark that, what's HPE's direction in all of this? We're really focused on quantum system integration with these HPC systems. So with that, I will pause for any questions. And thanks very much. I'll be quiet and drink some water, and let's see if there are questions for me or Namit.
Andrea, go ahead.
I do have a question, but I already asked two. So if anyone else wants to ask, I'm happy to defer my turn.
It's okay, go ahead.
Thank you, Michael, for this presentation. So you have a lot of numbers for latencies, but I think for the control stack, I don't think that for us latencies are so much of a trouble. Do you have estimates on throughput? Because, for example, for mid-circuit measurement, one of the challenges that we face in designing systems is it makes a lot of difference if you want to do mid-circuit measurement on all of the qubits, because that means you have to send data from all of the control lines back to the central processor inside the box. So I was wondering if you have any numbers as to what requirements you will need.
Yes, I think that's a good question. I don't have numbers like that, but I will point out that in fault-tolerant quantum computing, we'll be doing measurements all the time on almost all the qubits, maybe half of them or something, these ancilla qubits that are in the error correction code. So whatever has to happen in order to make that work within the control system is sort of happening within what I call, in my pictures, I was calling the quantum resource. So that all has to happen, has to be figured out. But it's assumed in my discussion that we'll be able to handle a lot of those measurements. And then at the logical layer, it won't be a big deal to do logical measurements in addition to those measurements that we're continually doing in order to make the error correction work.
Okay, sure. I agree that could be like the end target, but if there was like a middle point where you would say like this is enough for like the next 3 to 5 years before we reach fault tolerant, that would be nice.
Yeah, I don't have anything like that at the moment, but thanks for your question.
Thank you.
Quick question about the approximating sequences. Did you guys have any like data throughput in mind, like how much data is actually being transferred as the problem you're solving grows?
Right. This one isn't, the latency is highly relevant, but the amount of data transferred is not so much. The approximating sequence is likely to be on the order of 300 gates. So you might, need to send, let's say 1,000 bits, right? To send the approximating sequence in terms of these externally conditional bits. So it's not a whole lot. And similarly, those measurements, it's like we're sending a bit. But it's the latency that matters here. I would expect that any kind of network that isn't a pigeon would be able to handle the bandwidth.
And sorry, you also had a diagram with I can't remember the exact example now, but it had like a big data store and it's transferring to the quantum resource.
Yes.
For that one,
let me get to that picture.
Yeah, data sampler. Yeah. Do you have an idea of what that data flow is like?
This one's pretty similar in that the data sampler is going to be looking at some large amount of data, however it is randomly sampling from it. And then the connection to the quantum resource is sending a bunch of bits at a time. But here the latency is important. This whole Oracle sketch algorithm's usefulness will depend on how fast you can make this interaction. Because if it takes, 5 minutes to send each data point, then we won't be able to get enough data into the quantum computer for the algorithm to be useful, or something like that, right? But the usefulness will depend on how fast. So we want the latency to be minimized to give that algorithm its best chance to be solve problems.
Anybody else has questions? Yeah, I'll put in one last one. When you go back to the last slide, you're talking about how it's going to look, and you showed that comic or whatever, like that. Yeah, this cartoon. Do you actually expect it to be that close, or is it something that sort of like what's deployed here at Oak Ridge would work, where you have something, in a different building than what we have?
Yeah, I would expect it would be totally fine to have it on a different floor in a different building or anything like that. We can make high performance networks across buildings. That's not really a big deal. I would suggest we plan for some kind of high performance network and plan for something that's got point-to-point latencies, from end to end in the microseconds rather than milliseconds.
Any other questions?
Yeah, question on the previous slide, on the data sampler, how fresh and, is the data from which you're sampling? Yeah, sorry for making you, in this one, right? So, if it's relatively, previous runs or something like that, that's relatively stale, loading and filling is not a big deal. If it's something that's based on the computation on the same circuit, probably might be harder, more stringent requirements.
Broadly speaking, I don't know the answer to that. I'd refer you to this paper. I think I would bet that the answer is it depends on what you're doing. But in this paper, they're suggesting that they can work with any large data set. So it could be, something that you put in a few terabytes of memory and start sampling from, or it could be something that we have some computational process to compute. And I don't know which of those cases are most likely. And I think we'll learn more over time as people become familiar with this work and think about how it might be applied.
Okay, thank you.
Earlier in the talk, I think Namit kind of hinted that FTQC will impose some different scheduling requirements on the resources. That wasn't really covered in the talk. Do you have like 2 minutes, maybe a minute, to kind of describe what you meant there?
Right. Let me see if we actually have a slide. It's a good thing we deleted all the backup slides, so that's always helpful. Let me see if I have a scheduler, at least a sketch for what the schedule. Perfect. Okay. So this is an old slide, so let's say not the one that I wanted to show, but I think it'll do the job for now. But I think this is a good sense of how these things actually look like. And you have basically in general, you submit your job, you submit some quant program, you do circuit synthesis, and a lot of what this kind of FTQC compiler has to do is imagine that whenever, like, for example, as Michael was saying, okay, you need to compile these rotation gates, and the way these rotation gates are actually applied is that you imagine you take a subset of your qubits, you allocate them for the specific task that they're preparing some quantum state at a certain rate, you teleport it to the place you actually want to consume it, and then you do some operation. So it's basically this notion of quantum gate teleportation, where imagine a patch of qubits in your QPU is reserved for what is called distilling magic states. and then you move them over to the place that you actually want to consume them, and then you whenever you had to do a rotation gate, you consume it, and you effectively apply the rotation gate. So this kind of thing uses some kind of nice intermediate representation for your QEC system, and you're going to have basically explicitly allocated what are called distillation factories and so on, and some number of qubits, and you're always kind of bringing them to where the compute is happening. So you can think of them as like a separate part of your QPU with, and then there is the computational regime. So you bring them here, consume them, compute. Does that help, or I can go into maybe a bit more detail?
No, I think that's good. I think that's good. Thank you.